Okay, guys, uh, the Bohr effect and the Haldane effect have a bad habit of confusing students. And over the years, I have recognized the fact that more explanation is generally needed. And that's the purpose of this video. Um, the reason I've picked these two figures is they emphasize two basic facts about these two things. The first is that these both of these effects are basically the same effect. It just depends on what point of view you're looking at them from. Whether you're looking at them from the point of view of oxygen's effect on carbon dioxide, or you're looking at it as an effect of carbon dioxide's effect on oxygen. The second reason is I wanted to emphasize the fact that these two effects actually optimize the system for both carbon dioxide transport and oxygen transport. So the first thing I wanted you to do, this figure on top is very nice, and it summarizes a very important reaction in respiratory physiology, and that's this bottom one here involving carbonic anhydrase and the relationship between carbon dioxide and oxygen. All right. Let's consider the Haldane effect first. If you, or the Bohr effect first, excuse me. If you want to look at the Bohr effect, start with carbon dioxide in this equation right here on top. Okay. The Bohr effect says that high carbon dioxide has an effect upon oxygen binding. And in fact, what it does is it decreases oxygen binding. And this has a tendency to cause hemoglobin to release oxygen, which is something that you want when you're in the tissues. And of course, when you're in the tissues, that's where carbon dioxide is highest because that's where metabolism is taking place. Oxygen is being converted to carbon dioxide. It's being released back into the blood. And as the carbon dioxide concentration is high, you also want a condition where you're going to release more oxygen. Okay, so high carbon dioxide combines with water and leads to more bicarbonate, which has an effect of transporting more, allowing you to transport more carbon dioxide. And it also generates protons. Okay, protons combine with hemoglobin. Okay, and when hemoglobin is bound to protons, it does not bind oxygen as well. Okay, and so the net effect is to cause a release of oxygen and an increase in oxygen released into the plasma, which of course is taken up into the tissues where it's needed in this particular spot. So you've released oxygen from hemoglobin, which the tissues need, and you've picked up more carbon dioxide in the form of bicarb, which is what you need in the tissues as well. So the Bohr effect optimizes both carbon dioxide transport and oxygen transport when you're in the tissues. And of course, when you're in the lungs, the opposite is true. You have low carbon dioxide, and that causes more oxygen to bind to hemoglobin. And so the equation works the same way in the opposite direction, okay? And that, of course, is what you want. You want to pick up more oxygen, and you want to convert more bicarb to carbon dioxide where it'll be blown off in the lungs. And that's how you get rid of carbon dioxide. All right? So that's the Bohr effect. For the Haldane effect, we're looking at this from the point of view of oxygen's effect on this system. So we'll start at the lungs, where I ended with the Bohr effect. More oxygen binds to more hemoglobin, which tends to knock off protons, okay? So you have more protons, which combines with bicarb to generate more carbon dioxide gas, which is blown off in the lungs, okay? High oxygen tends to lead to a decrease in bicarb and a decrease in carbon dioxide content, more gaseous carbon dioxide, which is blown off in the lungs as it equilibrates with the CO2 in the alveoli, okay? This is what you want in the lungs. The Haldane effect gives that to you. And you'll notice it's exactly the same effect equation. And in fact, for all practical purposes, there's the same effect. It just depends on whether you're looking at bicarb content and the effect of oxygen on that content, or you're looking at the effect of CO2 on oxygen. And in this case, high CO2 leading to oxygen release, okay? Which is what you want in the tissues. So when you look at our two effects here, when you're looking at the Bohr effect in high CO2, that's this curve, you have less oxygen in the blood because it's been knocked off of hemoglobin and it's gone into the tissues where it's needed. So high PCO2 would represent the conditions that you have in the tissues. It's exactly what you want. It's exactly what you want for oxygen, and it's exactly what you want for CO2, where you're increasing the bicarb and you're increasing the total content. And that's shown here when you look at the Haldane effect. If we have high oxygen, as we do in the lungs, look, our CO2, our total CO2, is down, and that's because high oxygen tends to cause less bicarb. More carbon dioxide gas, which equilibrates with the alveoli, is blown off. The net effect is to decrease carbon dioxide content, mostly in the form of bicarb, which is where most of the carbon dioxide is. Okay, this is what you want in the lungs. Okay, in the tissues, low oxygen leads to a higher total CO2 content because you're increasing the amount of bicarb. Okay, that's what you want in the tissues. So these two effects, basically the same thing. They're the same equation. It just depends on what point of view you're looking at it from. And again, they optimize what you want depending upon whether you're in the tissues or the lungs. They work for you in both places. Okay?